first question, not many students got the first one. Correct answer is option 1, 4. A, option 4. Most of you gave me 6. Option C, 6. You can easily see 6 is not a good answer. Because to get a 6, you just apply Horner's rule. Right? You didn't take advantage of the special structure. Here, we only have even terms. We don't have odd terms. Only with even terms can you do a little better. Right? You need to take advantage of the special structure. So here, one way, in order to reuse our resource, remember the principle here, how can we save computation resource? The principle here, reuse our resource as much as we can. Here, this resource, x squared resource. X squared, we need a 1 multiplication. To get x squared. So we should reuse it as much as we can. So we store it in a variable here, let's use y here, right? Then we can rewrite the original polynomial as a0 plus a1y plus a2y squared plus a3y cubed. After that, then you apply Horner's rule. But this time, you bring down the degree from 6 to 3. When you reduce the degree number, at the same time, you reduce the number of multiplications by Horner's rule. So this computation, you need the 3 multiplications. Okay? Yeah. So the total, 3 plus 1 equals 4. Okay? Yeah. That's simple. But only a small number of students gave me 4. Most of you give me 6. Give me if. So here, because basically, if 5, I give you partial credit 2. If 6, I can only give you 1. Sorry, minus 3, right? Partial credit. Second one, also, many of you probably. I asked them about 1/2 of, at least 1/2 of, missed the second question. The answer is true, but more than 50% gave me false. Here, I try to make the wording to give you the impression it couldn't be true. So here, I try to use some way, if you answer this question just by your intuition, very likely you cannot get a correct answer. Nobody can find a solution to find the minimum of minimum in an element array with fewer than n minus 1 comparisons. Okay, this is the key point. Fewer than n minus 1. That means less than or equal to n minus 2. Less than or equal to n minus 2 comparisons. Right. even after 100 years. Here I use this number, try to give you the impression that because this is a long period, so someone very smart probably has a chance to do it. So you may get that kind of impression. That's wrong, because we proved it rigorously, n minus 1 is the optimum solution. Our proof will treat it very rigorous. Our proof. Right? So we prove we have proved that n minus 1 comparisons is optimal. Okay? That means nobody can do better than that. Right? Yeah. So you need to base on that knowledge. Okay? That knowledge. Sometimes I may, in my wording, I try to confuse you a little bit. I try to add some noise, okay, to check if your understanding is very solid. Something like noise. You need to remove the noise by yourself. Like this question. This 100 years, like some noise. Try to trick you a little bit. Number 3, good. Everyone got this one. Number 3. Number 4, option C. Yes. Many students pick A. So here, those students may feel ascending order array, probably you can do better. Here, actually, I told about this question before. Here, we implement the linear search. The algorithm is already there. It is fixed. We cannot switch to binary search. Okay? Just the linear search all the time. So under that condition, even the given array is in ascending order, you cannot apply binary search. Only way you apply binary search, you can do faster. But if you apply the linear search, you cannot do faster. Right? In the sense of average case efficiency, best case efficiency, worst case efficiency. Here, in this situation here, based on the context, we like to use the average case efficiency. Okay. Average case efficiency.
Just saying, you wanted to get in James' trouble.
Oh, yeah. Oh, James' trouble. Yeah. Oh, thanks for reminding me. All right. Yeah. Okay. Very good. Yeah. And all right. So that's this question. Number 5. Number 5 answer is true. But a few students give me false. Those students here, that's the case. If you didn't follow our content closely, if you only answer this question by your intuition or your basic logic in your mind, not using our special properties. This question, you need to be familiar with the special properties about inversion, right? Inversions. All right, so here, adjacent inversion. Those students probably they are not familiar with inversions. Adjacent. If you just by the logic, you may get intuition. It may not be true because adjacent inversion, no adjacent inversion may not imply no global inversion, right? That's two different things. How can you equivalent those two things? Different. But in the context, we need to connect to our context. In the context, no adjacent inversions means the data is ordered, right? So this condition implies that the array is ordered. Otherwise, we have to have at least one adjacent inversion. If it's not ordered, we have to have at least one adjacent inversion. That problem, okay? But if the array is ordered, then it implies that no global inversion. Right? So this question tells us if you answer your questions completely based on the general logic, it may not be reliable. Because when you apply the general logic, you may miss some critical properties, some important properties. You may not make use of those properties. Here, the property for the inversions you didn't use. Then, by your general logic, if you miss that property, then you do deduction by the general logic. It's not reliable. Okay? You may get a wrong conclusion. That's example here. Okay? So you have to be familiar with our course content. The properties, all those properties we have learned, that's the base for your deduction. Right? You need to have some base to do deductions. Here, you miss that important point. You miss this question. Okay? For those students. All right. Number 6, pretty simple. Here, I just use the asymptotic notation language a little bit. Okay? Check your understanding. Here you can see, I didn't give you many asymptotic questions, asymptotic notation questions. Actually, I should give you some asymptotic notation questions. But, the first time, I could not. I need to give you a few more asymptotic notation questions to make you feel more comfortable. Finding the minimum of an array with n elements. We know we have to answer n minus 1 comparisons. All right, so that's the absolute, accurate answer. But when you use asymptotic notations, you ignore the minor terms. And then you can also ignore the leading constant. But here it's 1. So it is in big theta. Okay? That's it. The good thing is most of you get this one. Most of you. You're fine. But I just feel some students may have some doubts. Okay? May have some doubts here.
Number 7. Yeah, this one, the answer is 7. The answer is 7. But so many students give me different answers. About 1/2 of the students give me 7. You need to do some work. Okay? Actually, there are 2 ways. Most of you use the repeated square, but it's also possible to use repeated cube. Both ways you can get 7.
Oh,
Here I can show you, yeah, because still many students miss this question. So let me show you the details. Repeated square. We try to use power of 2 to write this number 38. 38 equals, let's use power of 2 to write it. 32 plus 4, another power of 2 plus 2. Okay? So here, let's count. 32 equals 2 to the 5th. So that means we need a 5 multiplication to calculate 30 x to the 32nd power. Okay? 5 multiplications.
Would that be 4 or 5? It would be like 2 times 2. Wouldn't that be 4 multiplications?
All right, this is a good question. So here, you ask me if we n equals 2 to the k, then we calculate x to the n. You ask me k minus 1 or k multiplications. Answer is k.
Oh, okay.
Why? The answer is k. Because when k equals 1, two, that's 2, right? N equals 2. X squared, right? X squared, you need a 1 multiplication, right? 2 to the first. Exponent is 2 to the first. Exponent, all right? You look at exponent. So x squared, 2 to the first. Then 2 squared, 2 cubed, and so on. Okay? Yeah. So you get 2 to the k. Okay? All right. Yeah. But when you calculate x to the 32nd, you went through x squared already, right? You pass it, right? So x squared, you store it. Don't waste it. You keep it. Store it somewhere, okay? Don't throw away, because we need to use it later. X to the 4th, you have it already. Store it. Keep it. Do not recompute it. All right? Yeah. So then, x to the 38th, x to the 32nd, times x to the 4th, times x squared. But for these 2 operands, no new multiplications. No new multiplication. The new, only this is new, and then this multiplication is new. Right? Yeah. Only calculate the new multiplications on top of the first round 5 multiplications. So that's why the answer equals 5 plus 2. Okay? In that way. Try to use your resource efficiently. Okay? Avoid any redundant calculation as much as you can. Okay? Yeah. That's the repeated squaring method. there is a repeated cubic, but here I just point you to the direction. So we can also write 38 as 36 plus 2. 36, how to write 36? 36 equals 9 times 4 plus 2. 9, we can use repeated cubic. Okay? 9, we can use repeated cubic. In this way, you also get 7. All right. Yeah, but sometimes there are some cases. Sometimes one way could be better than the other. One way, one of repeated cubing, squaring could be better than the other.
What did you write there?
Oh, sorry.
About that repeat, right?
Repeated cubic.
Repeated cubic.
Cubic, yes. Very small. Repeated cubic. All right. Let me. Let me write here. Calculating this. Okay. So that is x cubed times x cubed times x cubed. Sorry. Okay. But when you calculate x cubed, you need to calculate x squared first. Then x squared times x. This square you need to store it because we need to use the square here. All right. Number 8. No. Not a good idea. Almost all of you, as I know, I couldn't remember anyone missed this one. But number 9, many of you missed the number 9. Answer is D. But many students give me C option. It is, the formula is in the notes. You just go there, check, find the formula. So you get these 4 points. Yep. So those students, quite some students, they missed this question. Easy question. So easy. Q, that's the quotient. And in our formula transformation, nothing to do. Besides reduction, there is nothing to do with the quotient. Quotient. So the quotient thing, in our discussion, the quotient has no effect. Has no effect on the common denominator, common factor, common divisor, Quotient. Also, the integer part has nothing to do with the common divisor of numerator denominator in our formula transformation. So here, in your understanding, you need to follow our development story. So in class, so you follow the story closely. That's very important because you understand the logic. You do not have to memorize the formula in a hard way because if you know the logic, you can memorize the formula in a natural. You know, the quotient won't impact the common divisor. So you should not choose this Q word, Q formula, Q related formula. Okay? All right. Number 10, it's a big one. The answer is 7. But many students give me either D or either B. Yeah. So here's the question. This one is harder than the first question, but you need to do it based on question number 1. Some students just did it directly without using the corners. That's not good. We need to use corners as much as we can. Because corners is a very efficient method. If you try to avoid it, or if you do not realize to use it, most of the time, very likely, you will do more work, not less work, more work. Here, it's an example. All right. First, this time, we need to factorize x cubed. All right, yeah, factorization. Then, a1 plus a2 x fourth, 3 x eighth, 4 x to the 12th. Then, inside the parenthesis, you can see the basic part, x to the 4th. So that's the similar structure to that of the question 1. So you can use another variable y. X to the 4th. You need to calculate x cubed. You also need to calculate x to the 4th. So let's calculate both of them. First, x times x, we get x squared. That's one multiplication. After that, we try to reuse this x squared. Okay? X squared times x, we get x cubed. One more multiplication. X squared times x squared, we get an x to the 4th. One more. Right? So we, in this preparation round, these are the preparation round. We use these 3 multiplications. Okay? That's the preparation. Then, next line. All right. Inside the parenthesis, we already have the y value. We just apply Horner's rule directly. So we need so here we need 3 more multiplications by Horner's rule. 3 more. Degree 3. If we use y as variable, it's degree 3 polynomial. Okay? Degree 3 polynomial. So 3 more multiplications. Then, don't forget, there is another multiplication hidden one here. Some students give me 6. Probably they missed this hidden one. Okay? This one more. All right. So total 3 plus 4. Sorry, 3 plus 3 plus 1, right? 3 preparation, 3 Horner's rule, then another one for our factorization, x cubed factorization, another one. So you can set. Okay? Yeah. Try to understand question number 1, not number 10. Well, in the midterm, you will have 2 similar questions like these 2. Don't miss that. 8 points. Okay? 8.
10.
Yeah, 10. Number 1, number 10. Definitely you will have 2 similar questions. Right? Midterm, 20 questions, each one 4 points, and 20 base points. Alright? 20 points free. 20 points free. 20 base points free. Alright? Then, 4, each one 4. 4 times 20, 80 points. 80 plus 20, 100. 100 points. 100 points. Midterm. Alright, these 2, don't miss these 2. Alright? I modify slightly. The basic structure is the same. The idea, principle, exactly the same. But you have to see some different numbers. Okay? You have to see some different numbers. Alright? Yeah. Prepare for that. Question? Mahmoud?
Zoom it little.
Zoom a little bit. Like that? Like
Yeah,
that?
yeah, thank you.
Alright. Alright. Yeah. But I need to move around. Alright. Alright. Number 11. Most of you did well. Option C. Because you only need to, because one student gave me B. B is the highest. B, exponential function, highest. One student gave me B, right? Yeah. Probably read the question carefully. Lowest order. Don't choose the opposite, highest order. That student probably confused with the highest order, right? Yeah. Read question carefully. Also important. And the first one, we know, degree 1, degree order also 1, but this is lower than, because log n is at a denominator. So the 1 at a numerator, but you have some variable part, a log function at a denominator, so the numerator 1 should be reduced. So you can treat this degree as 1 minus something. Okay? So 1 here, but this one is 1 minus. Definitely 1 minus is less than 1. Okay? If you do comparison, you compare it in this one. That's 1 minus something. Okay? Minus small number. You do not need to know how much is that small number. Just small, non-zero. It must be non-zero. Yeah. 1 minus non-zero number. Positive. That's the positive. Yeah. Number 12, A, but a few students, small number 2, about 2 students, gave me option C. We know, even if the exponent is very small, it's a positive number. So eventually, it will overcome that log function. Later, we have another one I will show you. Later, I gave you a similar one. So you can do the comparison. Number 13, option A, but a few students, 2 or 3, gave me option A. Those students, one thing, they didn't follow our notes, our course well, lecture well,
Because in the class I emphasize this a lot, right? When you sit in the class, I think you all know it. But a few students, they never show up. As I remember, there were 3 students who never show up. Number 14, answer is A. Only one student gave me option A. So here, because you can see A, x1 less than 3 elements, right? x2, x3, x4, 3 elements. The median can only be less than 2 and greater than 2. The median is in median of 5, right? 2 less than the median, 2 greater than the median. So the median can only be less than at most 2. Okay? But here x1 less than 3. At least 3 can be eliminated this way. Number 15. Most of you got this one, 84. Because if you count the square, 7 square plus 5 square plus 3 square plus 1 square. Okay? Yeah. So by our the way we use it. But one student, only one student, did in the wrong way. So I like to really, try to help you avoid that. That student multiply 2. Don't do it, okay? Yeah. So because we have one question, 2 black squares at its 4 corners. In that one, we multiply 2. But that one, remember, we have some symmetry. Symmetry along the diagonal. The reason we multiply by 2, because there is a symmetry by the diagonal. Okay? So you need to know why we multiply by 2. The mirror, flip. Okay? Flip. Mirror. Put a mirror on the diagonal, then you do flip. So we have another set of similar figures. But this one, we don't have that property. Okay? This one, we don't have the property. If you flip along the mirror, the diagonal, you get the same set of squares. Same set of squares. You do not get a new set of squares. You get the same set of squares by this after flip. Symmetry. Symmetric flip. So you should not multiply by 2. Okay? So here, when you do something special, you need to know why do it. Why we do it. Okay? Here we don't have that property, so we should not do it. Fortunately, most of you didn't multiply by 2. Doing the right way. All right. Number 16. The answer is B. Answer is B. Although many students pick a B, well, I feel they may not know how to calculate the value of B. I saw they tried to do the calculation on their paper, but I couldn't see the correct calculation. So here, I want to show it. Because I believe most of you couldn't do it. Most of you couldn't do it. Right. The first one is easy because log base 10, exponent number base 10, and the log base 10, there is some cancellation. Something like cancellation. So the first one, you just get 10 to the 10. 10 to the 10. Okay? Because this number you treat it as one single number at the exponent. Okay? Then, because the same base, log of base 10, 10 to some, n, let's say, then, by logarithm property, because we can bring the exponent number to the front, logarithm property, log 10, base 10 of 10, that's 1, that's n. The n here is 10 to the 10. That's the first one. The easy one, easy one. The second one. Now, most of you couldn't get the computation correctly. 10 to the 10 to the 10. The whole number to that 0 thing. But how about we write as 10 to the negative 6? That's better. We use base 10. We use base 10. So the calculation is easier. All right. You just treat this exponent as one number, external exponent one number, internal exponent another number. Two different numbers. Then by the property, two numbers should be multiplied as the new exponent. Okay? Yeah. Then 10 to the 10 to the 4. 10 minus 6 is 4. 4. Okay? Yeah. 10 to the 10,000. 4 zeros. Okay? 10 to the 10,000. Compare with 10 to the 10. Exponent. If you only compare the exponent numbers, 10 versus 10,000. Only compare exponent. 10 versus 10,000. Which one is fine? Here, I use concrete numbers to make sure that power function form can easily beat the logarithm, even if the exponent number is very small. Can easily beat it. 0.6 digit after the decimal point, easily beat the logarithm. Okay? With this concrete example. All right. Number 17. Answer is true. Answer is true. A few students give me false. Not many. About 3. About 3 only give me false. 3 or 4. Okay. Here, not in place. You need to imagine the situation. So some students, give me even odd cases. Even odd cases. Actually, you can consider if 2 elements n greater than 1, 2 elements, you just swap 2. But another way, here we need to construct concrete examples to have certain property. Here, in order to convince yourself, you may need to construct concrete examples. Here, I like to use circle. Okay? Circle to show the way to do construction. Let us draw a circle. Okay? Let us arrange our elements along the circle. A10. 1. Okay? Then you change the position clockwise. Shift one position clockwise. How about that? One position clockwise. Then after the shift, all elements are not in place. Okay? First, you put them all in place. Okay? First, you put all elements in place. Then, after that, rotation. Okay? Yeah? Do rotation. One position to one direction, counterclockwise, clockwise, just the one direction. One of the directions. Yeah? Then, none of them is in place in this way. Constructing appropriate examples. Many times we need to do things like that. All right. Number 18, easy question. Almost all of you got this one. 1/2 times 20 times 19. Number 9, minimum value 2, but a few students gave me 1. You need to look at, if only one element is not in place, how can that happen? All the remaining n minus 1 in place, then the last one has to be in place, right? They forgot that part. So if you have the minimum number of elements, that must be 2. At least 2 elements in place, not in place. All right. Number 20, most of you got this one, but small number, 2 or 3, missed this one. Answer is 3, 7. Here we use the formula, n1 equals 2 to the n1 minus 1, and 2 equals 2 to the n2 minus 1. You add up, n1 plus n2 equals 2 to the n1 plus 2 to the n2 minus 2 equals 134. So 2 to the n1 plus 2 to the n2 equals 136. Then do factorization. 8, all right? Factor power of 8 as much as you can. 8, 1, 7, 17, you write it as 1 plus 2 to the 4th. Okay? So you get 2q plus 2 7th. 2q plus 2 7th. Okay? All right. One student wrote n to me. All right? One student gave me n1, n2. Read the question carefully. All right? So we need the n1, n2, not the n1. Good. So read the question carefully. But only one did that. All right. Number 21 answer is 130. But still, quite some students missed that one. 4 or 5 students missed that one. Just 135 minus 5. Because we only, when we do elimination, so here, we still, when we do comparison, we eliminate, every time we eliminate 1. After 130 eliminations, there were 5 elements left. And we know there is one, one element that is greater than these 130. There is one, we know that, the current minimum, okay? Current minimum may not be the overall minimum, the current minimum. We have that number, current minimum, in our hand. And the last 5 elements remain. So
that must be bottom 5. That must be bottom. The 1 current minimum must be in bottom 5. That understand. That understand. Okay? All right. Number 22, answer 35. Quite a few students didn't give me 35. Why 35? First, do not look at this condition. X5 is not in place. That condition. Okay. Skip that condition temporarily. Yep. If you skip, the answer is maximum number is 1/2 times 9 times 8. So you get 36. If you skip that, 36. All right. But that this situation corresponds to descending order. Descending. The data is in descending order. When you look at a descending order, X5 in place. X5 in place. So you have to change it. Okay? You have to change it in place. How to change to move it out of place? All right? How to change it to move it out of place? Switch with one of its adjacent elements. Okay? You can swap. X4, X5 adjacent, or swap X5, X6. Because after you make that swap, you reduce inversion by 1 from that particular pair of elements, only that one. But for others, no change. For other, when you consider pairs with others, no change. X5 with others, because their relativity order keeps the same. X6, if you compare with others, their relativity order the same, right? Yeah. Think about that. Imagine that situation. Okay? Yeah. So you need to know why you get 5. Why you get one inversion reduction is sufficient. Because of that reason, of the adjacent swap. Okay? All right. 23, two comparisons. Many of you give me one. One is for the best case. Why those students give me one? They compare X2 and X3 and they tell me X2 less than X3. But think about why not X2 greater than X3? By adversary argument, you should get this case, right? By adversary argument. You should get X2 greater than X3, not less than X3. Less than X3, you get the best case. But we want the worst case. Okay? So to do comparison, the first comparison should be X2 and X4. Okay? There is winner the largest. Okay? Winner largest. Okay? Let's assume X2 less than X4. Okay? So the second comparison, x2 and x3. The winner here, second minus. Okay? Because we don't need to consider x1. x1, the first round loser, so cannot be considered. Okay? Because x2 already beat it. This way. All right. Yeah. But so this question, from this question, you should know. From this question, you should know how to find the second smallest in a 4-element array. Can you see it? We have 4 elements. The first round we do comparisons, these 2 parallel comparisons. After that, we do 2 more, so we can find second smallest. Here, I point this out because in the midterm, I will give you a question closely related finding the second smallest element. Okay? Not directly. I won't give you direct question, how to find second smallest. That's too easy. But indirectly, okay, part of the question, you need to find second smallest. Right? So the whole question it looks different. The whole question looks different. But when you do some first round processing, the second round, you need to solve this. Okay. All right. Okay. So when you do preparation, you have more than 1 week, right? When you do preparation, get familiar with this question. How to find the second smallest numbers. Okay? Number 24. Number 24. This is the hardest one in this assignment. Hardest. All right. Answer, solution, yes. Let me tell you how. How? Some students very close to this final solution, but still, one critical step, they missed critical part. So the right way, the first comparison should be very careful. Okay? First comparison. Do not do comparison with x1 involved. Most of you, the first comparison with x1 involved in the first comparison. Don't do it. Okay? The first comparison, compare x2 and x3. Leave x1 out, the second round. So one must be greater than the other, right? So let's assume, we can assume x2 less than x3. Okay? One bigger, one small. The second round, now we can use x1. Then you are in the driver's seat. Okay? All right. Second round, compare x1 and the larger one, x3. Not a smaller one, larger one. Okay? Then you have 2 cases. x1 less than x3. Because we know the minimum is less than x1, less than x3. So x1 is the solution. x1 is the solution, right? Another case, x1 greater than x3. Now you have combining with the first comparison. x2 less than x3 less than x1. So x3 is the solution. How smart it is. Okay? This way. This is the smart solution. This is the hardest question in this assignment. But, not too hard. Not too hard. All right, the last question, we run out of time. Answer A1, A2, and B3, B4. Correct answer. Many of you give me correct, but you need to tell me why. Because A1, A2 less than, how many of those? A3, B2, B3, B4. So they're greater than at least 4 elements. B3, B4 greater than A1, A2, B1, B2. They're greater than at least 4 elements. In that way, you convince me you have a solution. But many students missed this critical part. Okay? These two critical parts. Then you cannot get full credit. So I need to see, these two critical conditions. Okay? Critical properties. All right, that's it. So loop preparation.
Can you go back up? I want to see 24 again.
All right, good.